Hello guys, welcome back to another video. Now in this video we're going to be looking at how to derive a common circular motion equation. A is equal to v squared over r. We're going to be trying to derive this. We're going to be looking at this or deriving this from the perspective of the circle I introduced in the former video, where I said the circle is not like this. It's not something perfect like this with a circular circumference, like this, like curved circumference, but it's something more like this. So having this in mind, so if you're looking at this particular shape, what this simply is this, but where you have multiple triangles making up this, what you would call your circle. You've got multiple triangles. So such that if you zoom in, if you could zoom in down to the tiniest possible scale, you would find that this over here, this sides of the triangle, or this sides of these little shapes are straight. They're not curved, they are straight. So viewing the circle in this way, we're going to derive the what? We're going to derive the equation of the acceleration of an object that is circling, or that is going around the circle with a constant velocity v. Now how we are going to work with this octagon over here, or with this shape over here, applies, it still applies even if you have a shape with multiple triangles inside, like multiple isosceles triangles inside. It applies, it still applies. Say we've got a particle that is going right around this path. So say we've got our particle over here, a very tiny particle going around this path. And say now it's at this point. And at this point, it has got which velocity? Now watch my former videos in order to get how I get the velocity in this case. Remember in the former video on the circle, I mentioned that this particle which is going right around this path doesn't necessarily follow this path over here. It disappears from this point and appears at this point. Now, the moment it appears at this point, it has a velocity v, which is of the same magnitude, like looking at the magnitude of the arrow. The velocity at this point, that is the arrow, talking about the arrow now, this arrow has the same size or magnitude as this line segment over here. This line segment over here has the same magnitude as our velocity vector over here. Now, the velocity at this point can be represented by this arrow over here. When the particle is at this point, remember, the particle which is going right around our shape over here, or right around this path over here, is constantly experiencing a force that a lot of people would say is directed towards the center. So when it is at this point, it's still experiencing a certain amount of force. The force it experiences at this point is the force that is responsible for getting this particle from this point up to this point, such that when it is at this point, it now has a new velocity. Let's call this v1. At this point, it now has a velocity of v2. This over here being the resultant, if we're now using the vector rules of addition, this over here being the resultant, v2, so we can again label this as v2. Now bear in mind that this v2 over here, the resultant velocity v2, comes as a result of the addition of this v1 velocity here and the velocity imparted by the force acting on the particle on this point over here. And what is that imparted velocity? The imparted velocity can simply be found by joining these two arrows. And this way. And since we're saying this is the resultant of what? Of adding the initial velocity v1 and the imparted velocity, let's call the imparted velocity vi. Now the imparted velocity is simply the acceleration, guys. Please always bear this in mind. I call it the imparted velocity, but this is simply the acceleration at a single instance in time, like at the smallest possible unit of time possible. That is what this is. This, although you're looking at it from a macroscopic point of view, is actually something that is at the tiniest possible scale possible. Like, I'm working at the infinitesimal scale here. So what we have in this scenario is simply this. And let me rub this too. Completely unnecessary for what we want to do right now. So this is what we have. Now, let us say this angle is theta, and this angle over here is alpha. Now, if we extend this line segment over here, if we extend the line segment over here, we get something like this. And if we extend this line segment over here, we get something like this. Notice then that this angle over here is also equal to what? Opposite angles is also equal to alpha. But notice something again. We extended this line segment over here. If we extend this line segment over here up to this exact length, say it ends over here, we can again form a shape similar to this, whereby we're now going in, instead of going straight in this direction, we're now going in this direction. So we can have another shape like this, which is in a way touching this shape. So you have something similar to this at this point. We have something similar to this. This and that, where this is the alpha and this is the alpha over here. So this is this. So this is a part of our shape. If we were to complete it, we would go on and do this. What I'm saying in this case, we can form a shape similar to this shape on top here, where we've got what? In this case, we would have something like this, I believe. Something like that, where this would be our new shape. So picture this in your mind. Why am I telling you to picture this? I want to be able to justify what I'm about to do right now. So at this point, we've got our angle alpha. Now notice that if this shape over here is similar to the other shape you could form over here, this angle over here and this angle are equal. Now the total of these two angles over here is what? Is 360 minus 2 alpha. So 360 minus 2 alpha is equal to this entire angle plus this entire angle. That is 360 with the exclusion of alpha plus alpha. However, in order to get this angle over here or this angle over here, remember that the two are equal. In order to get this, what we have to do is simply divide by 2. So dividing by 2, what we get? We get 1/8 minus alpha. So 1/8 minus alpha is which angle? It's this angle, and at the same time, it's this angle. So it's equal to this angle over here, or this. But notice something now. because these are isosceles triangles, this angle over here is equal to this angle over here, and this angle over here is equal to this angle over here. Notice again that these isosceles triangles are equally divided throughout our circle, such that being isosceles triangles, right, this is equal to this, but are equally divided. This angle is also equal to this angle, and is equal to this angle, and is equal to this angle, and this angle, and so forth. So, having our 180 minus alpha, which is this angle over here, in order to get this angle, that is this, in order to get this, all we have to do is simply divide this by 2 now. So, we've got 180 minus alpha divided by 2, and what do we get? We'll get 90 minus alpha over 2. So, our angle over here is equal to 90 minus alpha over 2. But notice that our angle over here is also equal to our angle, that is this adjacent angle over here. This 90 minus alpha over 2 is also equal to this angle over here. Not just this, but this, and this, and this, and this, and this, and this, and so forth. Now, notice something now. We've gotten into this triangle now. We've now gotten into this triangle. Recalling that this triangle is an isosceles triangle, how would we find this angle using theta? That's simple. That would simply be 180 minus theta, giving us what? Giving us this angle plus this angle. So we then divide this by 2. If we divide this by 2, what do we get? We get 90 minus theta over 2. So 90 minus theta over 2 is also equal to this angle. So what we have in this case is this being equal to this. So we've got 90 minus theta over 2 being equal to what? 90 minus alpha over 2. I'm sure you now see where I'm getting with this. 90 over here vanishes, 90 over here vanishes, this negative sign vanishes, this negative sign vanishes, this half over here vanishes, this half over here vanishes, and we're simply left with what? We're simply left with theta is equal to alpha. So in this case, what I was simply trying to show is that theta over here is equal to alpha over here. That is, now I forgot something essential. This, remember we're picturing this as a circle. So there's line segments over here are of equal length. And let's label their length as r. That is the radius. So what I'm simply saying here in this case is that this triangle over here is similar to what? Is similar to this triangle over here. That is what I'm simply saying. This triangle over here is similar to this triangle over here. Now, notice that the magnitude of V1 is equal to the magnitude of V2. Why? Because our object is moving with a constant speed throughout this entire path. So, this side is equal in length to this side. And because these radiuses are equal throughout, this side is equal in length to this side. So we've got something like this. And these two angles, as we have just shown, are what? Are equal. So these two triangles are similar. Let me now rub this off so that we do the necessary math for the derivation of this equation now. Now the math is relatively simple, guys. What we simply do is recognize that these are similar triangles. So we use the rules of similar triangles, which I believe we obtained from Euclidean geometry. So in this case, we have what? The ratio of this side over here for this triangle the ratio of this side over here, that is V2. Let's simply put this so that we indicate that we're dealing with the length or the magnitude of this velocity. The ratio of this side to the ratio of this side over here is equal to what? Is equal to the ratio of this side, the imparted velocity, to the ratio of what? To the ratio of this side. So we've got something like this. So we end up with something like this. But what we're looking for, remember that I mentioned that this is equivalent to the acceleration. So what we're simply looking for is this. So the acceleration in this case is simply this, or at least the magnitude of the acceleration is simply this. Multiplying both sides by this gives us what? Gives us V2 squared all over what? All over r. But again, like I mentioned, this is simply the acceleration. Watch my previous videos to understand why I'm always saying this is the acceleration. So we end up with something like what? This being the acceleration, we end up with something like this. A. But remember that this is the magnitude of what? Of the velocity v2, which is equal to the what? To the magnitude of the velocity v1, which we can simply label as v. The magnitude being the speed, we can label it as v. So we've got A is equal to v, but it's a square, squared over what? Over r. So that is how we derive our equation for the acceleration of an object that is moving throughout a circular path with a constant speed of v over here.